Hello students, I hope you all are doing good. Today we are going to discuss NCERT section 10.6 to 10.6.2 of chapter Wave Optics. This is the disclaimer. So in today's lecture we are going to explore the fascinating topic of wave optics, specifically focusing on diffraction. By the end of this session, you will have a strong understanding of what diffraction is and how it occurs. We will start by looking at diffraction through a single slit, which is a classic example in wave optics. You will be able to understand how the diffraction pattern forms and what the intensity distribution looks like. Pay attention to the mathematical conditions that determine where the maxima and minima position occur in these patterns. Okay, so this is the index of topic that we are going to discuss today. So we are going to discuss NCERT section 10.6 first, that is diffraction. So diffraction is a phenomenon that occurs when a wave encounters an obstacle or a slit. Next, we will discuss the single slit diffraction, that is NCERT section 10.6.1. When light passes through a narrow slit, it spreads out and creates a pattern of light and dark bands. Finally, we will look at how we can observe the single slit diffraction pattern. Okay, by shining a coherent light source like a laser through a narrow slit and projecting it on a screen, we can see the characteristic pattern of alternating bright and dark bands. This pattern provides valuable insights into the wave properties of light. Okay, so our objective is to understand how light behaves when it encounters the obstacles. Notice the image showing light bending around the corners. Okay, so you can see that light is bending around the corners of obstacles. Okay, in the image, there is a door that is slightly open and light is coming from it. Okay, but you can see light is bent after passing through that narrow opening and it is illuminating the shadow of that door. Okay, in actual there should be shadow of door at the wall. Okay, and for small opening there should be small rectangular strip of light on the wall. But due to bending of light, due to diffraction of light, this light is bent and it penetrates into geometrical shadow of the obstacle. Okay, so let's examine what happens when light encounters an opaque object. If you look closely at the shadow it casts, you will notice something interesting near the edges. This is where diffraction begins to play a role, affecting the shadow's appearance. Okay, so close to the region of geometrical shadow, you will see alternate bright and dark bands, just like interference in Young's double slit experiment. Okay, so this shows that light can bend around the corners, allowing us to reach areas that would otherwise be in shadow. Okay, generally that areas there should be a shadow of that door. Okay, but due to diffraction, light is bending and it is illuminating the shadow. Okay, so the areas that should be shadow that are being illuminated by bent light. Okay, so this bending is a key characteristic of diffraction, demonstrating that light doesn't always behave as a simple ray. Okay, we discussed in ray optics that ray of light always travel in straight line. Okay, but according to wave nature of light, light bends around the corners of the obstacle or any aperture. Okay, so light doesn't always behave as a simple ray, especially in wave optics or when we see the wave nature of light. So understanding this helps us explain many optical phenomena. So let's explore what diffraction really means. It's the phenomenon where light waves bend around the corners of an obstacle or aperture So what is aperture? Small opening. Okay, spreading into areas that would otherwise be in shadow. Okay, we are illuminating any obstacle, any object we are illuminating, and there should be a shadow casted by the light due to that obstacle. But due to the bending of light around the corners of obstacle, light penetrates into the geometrical shadow of that object. That is the phenomenon of diffraction. Okay, so spreading into the areas that would otherwise be in shadow. This bending and spreading are the key characteristics of wave behavior. To truly grasp diffraction, we need to think of light as a wave, not just a straight beam. This wave perspective helps us explain how light can bend and spread, which is something a simple straight line model can't account for. So diffraction isn't unique to light, it's a general property of all waves. Okay, whether we are talking about sound, light, water, or even matter waves, they all exhibit diffraction. This universality highlights the wave nature of this phenomena. Diffraction becomes most noticeable when the size of the obstacle or aperture is comparable to the wavelength of the waves. Okay, so you can see the diffraction pattern more clearly, or diffraction is more noticeable when size of obstacle around which the light is bending or aperture. Okay, so that size should be comparable to the wavelength of wave, okay, of which diffraction is occurring. Okay, and we are taking, if we are taking simple light, that is a white light for diffraction, if we are considering that, so the size of obstacle or aperture should be comparable to the wavelength of the white light. Okay, so now we are going to explore the concept of diffraction through a single slit. Okay, our objective is to understand how light behaves when it passes through a narrow opening. Take a look at the image on the slide. It shows a diffraction pattern created by a single slit. Notice the central bright region and the alternating dark and bright bands. Okay, in the figure you can see the light beam is coming. Okay, a plane wavefront is coming, and after passing through a narrow opening, that is single slit. Okay, in YDSC Young's double slit experiment, we use double slit. In diffraction, there is only single slit. Okay, so very narrow opening. So due to that narrow opening, okay, light is emerging from that narrow opening, and we can see the diffraction pattern. What is the mechanism? We will see. Okay, and you can see in the pattern, the intensity of central bright region is much large compared to other bright regions, other secondary bright maximas. Okay, so there are alternating bright and dark fringes or bands like Young's double slit experiment, the pattern we observed in Young's double slit experiment. But here central bright region is much brighter in intensity as compared to other bright bands. Okay, so let's dive deeper into what happens when we replace the double slit in Young's double slit double experiment with a single narrow slit. When we shine a single color light through this slit, a unique pattern emerges on the screen. This pattern is different from what we see with the double slit. So first observe that there is a bright region in the middle of the pattern. This central bright spot is the most intense part of the diffraction pattern. It's important to note that this is where most of the light energy is concentrated. Next, notice the dark and bright bands on both sides of central bright region. These alternating bands are a result of the interference of light waves. The dark bands occur where the light waves cancel each other out, that is, destructive interference is taking place. Okay, while the bright bands occur where they reinforce each other, means constructive interference is taking place. As we move further away from the center, these bands become fainter. Okay, so we are not able to observe large amount of bands because intensity is fading out. Okay, so we can only see few bands. After that, intensity is decreased to such value it will appear as dark band, and we will not see alternate dark and bright fringe. Okay, so this fading occurs when the intensity of light decreases as the waves spread out and interfere over a larger area. So this entire phenomenon is known as single slit diffraction. It's a fundamental concept in wave optics that helps us understand how light behaves in different situations. So take a look at the image on the slide, which illustrate the geometry of path difference in this scenario. Notice how the light waves spread out after passing through the slit, creating a pattern on the screen. Okay, so figure 10.14, the geometry of path difference for diffraction by a single slit. Okay, so Ln is the single slit, and we have divided this single slit into 4 parts: Lm1, M1m, MM2, and M2n. Okay, so what is the path difference between the waves originating from L and N? It is NQ. That is the path difference. Okay, and on the right side of the diagram, what is being represented? The interference pattern. You can see the central bright fringe is brighter, and other secondary maxima are less intense than the central bright maxima. So let's delve into the single slit diffraction pattern. Our goal is to comprehend how this pattern forms and what it look like. We will start by considering a plane wave, which is a wave with constant phase fronts. Okay, approaching a single slit. Okay, this slit has a width labeled as A in the diagram, represented by line Ln. Okay, so consider a plane wave incidenting on a single slit of width A, that is represented by Ln. Okay, according to Huygens principle, every point on a wavefront can be thought of a source of tiny secondary wavelets. Okay, so the point L and point N can be taken as the sources of secondary wavelets. Okay, a plane wavefront is coming behind the single slit, and after incidenting on that slit Ln, the each point on this Ln slit will act as a source of secondary wavelet. Okay, so these wavelets interfere to produce a diffraction pattern. So wavelets originating from different points on this slit will interfere to produce a diffraction pattern on the screen placed at some distance. Okay, so pattern consists of central bright maximum, which is much wider and more intense, as represented on the diagram on the right side. Okay, so central bright maximum is much wider and also more intense than the other secondary maxima, separated by points of zero intensity. So these bright maxima are separated by the minimas, means dark fringes. Okay, so we are going to focus on how to find the intensity of light at different points on a screen. The objective is to understand the positions of maximum and minimum intensity, which are crucial for understanding wave behavior. Let's start by looking at figure 10.14. Okay, so again the geometry of path difference for a diffraction by a single slit is shown. Also a P point. We have to find that constructive or destructive interference will happen on P. Okay, so which type of interference will take place on point P, and what are the conditions for constructive and destructive interference in the case of diffraction. So now let's delve into the first step of our analysis. We want to determine the intensity at any point P on the screen. This involves identifying the positions of maximum and minimum intensity, known as maximas and minimas. These positions are where the light behaves constructively light waves constructively or destructively interfere respectively. Okay, so next observe how the line joining point P to various points like L, M and N can be treated as parallel. These lines make an angle theta with the normal to the screen, okay, which is MC. Okay, so they are making, you can see all these lines are making angle theta with the normal to the screen, that is MC. So MC is normal to screen and slit LN. So to proceed, we break the slits into tiny sections. This approach allows us to consider each section as a source of light waves. By doing this, we can analyze how each section contributes to the overall intensity at point P. So finally, each tiny section sends light. So we have divided the slit into tiny sections. So each tiny section sends light to point P. Okay, and we need to add up all these light waves. The key here is to consider how these waves line up with each other or combine with each other, which is determined by their phases. Okay, this is cumulative effect of waves phase determines the resulting intensity at point P. Okay, so how these waves originating from different sections of the slit will interfere, will combine. It will determine that what is the resulting intensity on point P. And we will see the condition for minima and maxima at point P. So let's examine what happens when light waves reach the slit. These waves are aligned and in sync, meaning they start off together. This synchronization is important because it sets the stage for how the light will interact as it passes through the slit. Notice how when light passes through the slit, all the rays that reach the middle of the screen travel the same distance. Okay, so when all the secondary wavelets, okay, that are originating from the different sections of slit, they will reach the midpoint of the screen at the same time. Okay, this is the key point because it means these rays are in phase with each other when they meet at center. If they are reaching at the center of the screen at the same time, so path difference will be nearly zero and phase difference will also be zero. So they are in phase or either phase difference will be constant. Okay, so for this middle point, phase difference is generally zero. So this in phase condition is what leads to the formation of a bright spot at the center of diffraction pattern. So because these light rays travel equal distances, they combine constructively to create the brightest spot at the center, known as central maxima or primary maxima. This is most intense part of the diffraction pattern. Understanding this concept helps us predict where other bright and dark spots will appear on the screen. So our objective here is to find the position of minima which are points of destructive interference. Take a look at the diagram of a single slit diffraction pattern. Notice how the light spreads out after passing through the slit, creating a pattern of bright and dark regions. Okay, now we will find the position of minima. Okay, so let's start by finding the angle theta for first minimum. To do this, we divide the slit as shown in the figure, which is labeled A, into two equal halves, A by 2, A by 2. Okay, so LM and MN. We have divided this LN slit into two parts. So this division helps us analyze how light waves from different parts of the slit interfere with each other. So now consider a pair of rays labeled LD and ME. Okay, which originate from points that are A upon 2 apart. So what is the path difference between rays between the waves originating from L and M? Okay, or we can say rays LD and ME. pair of rays. So what is the path difference? mg here. And these are originating from two sources, L and M, and these two sources are separated up by a upon 2 distance. Okay, so this pairing is required because it allows us to examine how light from different parts of the slit interacts. The path difference between the wavelets from the top edge and midpoint of the slit is given by a upon 2 multiplied by sine theta. So what is the path difference? So angle MLG, it is theta. Okay, so what is mg here? A by 2 sine theta. We can find sine theta from here. It will result in mg upon lm. Okay, so mg will be lm sine theta and lm is a by 2. So mg is equal to a by 2 sine theta. That is the path difference. So this path difference is essential because it determines whether the waves will interfere constructively or destructively. We can extend this concept by considering any number of rays pairing that start from a distance of a upon 2 from each other. Okay, like the bottom two rays in the diagram. This repetition of pairing reinforces the pattern of interference across the entire slit. Okay, any two pairs can be considered separated by a by 2 distance. Okay, like the bottom two rays, ME and NF. These two rays can also be taken. Okay. So for destructive interference to occur, the path difference must be lambda upon 2. Okay, where lambda is the wavelength of light. This condition ensures that wavelets from upper half of the slit cancel out with those from the lower half. This is the key to finding the position of first minimum. Okay, so wavelets originating from upper part of the slit, upper half, that is LM, should cancel out the effect of, or should cancel out, or should destructively interfere with the wavelets originating from lower part of the slit, that is NM. Okay. So our objective is to determine the position of first minima in this setup. Take a look at the diagram of single slit diffraction. So let's delve deeper into the concept of destructive interference. Imagine a ray of light emanating or originating from any point within the slit. For every such ray, there exists another ray at a distance of half the slit width, a upon 2, that can interfere destructively with it. Okay, this means that these two rays can cancel each other out, leading to a dark region or minima. Okay, so now let's quantify this interference. For destructive interference to occur, the path difference between these rays must be half the wavelength, that is lambda by 2. So what is the path difference? In this case, when we divide the slit into two parts, path difference is a by 2 sine theta. So this path difference should be equal to lambda by 2 for destructive interference to happen. Okay, so this gives us the condition a upon 2 multiplied sine theta equals to lambda by 2, which simplifies to sine theta equal to lambda by a. Okay, this equation tells us that angle at which the first dark fringe appears depend on the wavelength of light and the width of the slit. As a result of this condition, we observe a dark fringe or minima in the diffraction pattern. This is the key takeaway. The position of these dark fringes is determined by the interplay between wavelength of light and the slit width. Now our objective is to find the position of second minima. Let's start by dividing the slit into 4 equal parts, each of size a upon 4. This division is crucial because it allows us to apply the same logic where used for finding minima in diffraction patterns. Notice how breaking the slits into smaller sections help us analyze the wave behavior more precisely. So for the second minima, we replace a upon 2 with a upon 4 in our calculations. This substitution is a key because it changes the conditions under which the minima occurs. By adjusting the slit size, we can predict where the light intensity will be at its lowest. So now let's look at the equation lambda upon 2. Now the path difference between any two sections of this slit, which is divided into 4 parts, should be lambda by 2, so that they can interfere destructively to form the minima. Okay, so lambda upon 2, that should be the path difference, which is equal to, so now path difference between wavelets originating from two parts, from any two consecutive parts of the slit, which is divided into 4 parts, that is a by 4 sine theta. So this a by 4 sine theta should be equal to lambda upon 2. So here lambda represents the wavelength of light, a is the slit width, and theta is the angle of diffraction. Okay, so finally we solve for sine theta equal to 2 multiplied by lambda upon a. Okay, so this gives the position of second minima. Notice how the equation ties together the wavelength and slit width to determine the angle. Our objective is to determine here the position of nth minima in this diffraction pattern. This will help us understand how light behaves when it encounters obstacles. So let's start by considering the nth fringe. Okay, so when we used to find the second minima, we divided the slit into 4 parts. When we found, or we derived for the first minima, we divided the slit into 2 parts. Now we are considering the nth minima, or we are going to find the position of nth minima. So we can divide the slit into 2n parts. This division helps us analyze how light waves interfere with each other. Okay, why 2n parts? Because every two consecutive parts, wavelets originating from every two consecutive parts should have path difference of lambda by 2, and they destructively interfere and form the minima at some position xn for nth minima. Okay, so this division helps us analyze how light waves interfere with each other to create the diffraction pattern. So the condition for nth minima occurs when the path difference between wavelets from two ends of the slit is n times the wavelength. Okay, that is lambda. Now let's determine the angular position of nth minimum. This position is where the light intensity is at minimum due to destructive interference. Okay, so the equation a upon 2n. So what is the path difference between two consecutive what is the path difference between wavelets originating from two consecutive sections, two consecutive parts of the slit that is being divided into 2n parts? Okay, that is a by 2n sine theta. That is the path difference between two consecutive wavelets originating from two consecutive sections of slit. Okay, that should be equal to, so that path difference should be equal to lambda by 2. Okay, so this helps us find this position. Here a is the slit width, theta is the angle, and lambda is the wavelength. Okay, so simplifying further, we get get a multiplied by sine theta equal to n lambda. Okay, this equation is fundamental in understanding how the diffraction pattern forms, as it directly relates the slit width, angle, and wavelength. Okay, so now you can see, okay, why in the second bullet point it is written that condition for nth minimum is when the path difference between the wavelets from the two ends of the slit, two ends means from L and from N, from extreme ends of the slit. What is the path difference? A sine theta. When slit is not divided into any part, when we consider whole slit, then the path difference will be A sine theta. that should be equal to n lambda. That's why we have written in second bullet point that path difference between two wavelets from two ends of the slit is n lambda. Okay. But if we are considering two sections of the slit that is divided into two n parts, then path difference will be between two consecutive wavelets will be a by 2 and sine theta, which will be equal to lambda by 2. And after solving, it will become a sine theta equal to n lambda. Okay, since the angles involved are very small, we can approximate sine theta as theta. Okay, this simplification allows us to easily calculate the position of minima in single slit diffraction. So with this approximation, we can find that theta is approximately equal to n multiplied by lambda upon a. Okay, so it's important to note that n can be positive or negative integer like plus minus 1, plus minus 2, plus minus 3 and so on. However, n equals to 0 corresponds to central maximum and n equal to plus minus 1 correspond to first minimum. Plus minus 1 corresponds to first minimum. Okay, and n equal to 0 corresponds to central maximum, not a minimum. Now, our objective is to find position of maxima in this setup. Take a look at the image of single slit diffraction. Notice how light behaves when it passes through narrow slit, creating a pattern of bright and dark regions. Now we have divided the slit into three equal parts. That is a by 3, a by 3 and a by 3. So let's dive deeper into finding the maxima. To do this, we divide the slit into an odd number of parts. This division helps us analyze how light waves from different sections of the slit interfere with each other. Okay, so we will consider that the path difference between the wavelets originating from every section should be lambda by 2. Okay, then two parts, wavelets originating from two parts of this slit will interfere destructively. Okay, and it will result in zero intensity. But wavelets from one section of the slit will remain as it is because we have divided slit into odd number of sections. So wavelets or waves coming from one section of slit will remain as it is without constructive interference, without destructive interference. So it will illuminate the screen and form the maxima on the screen. Okay, that is the mechanism here. So let's dive deeper into finding the maxima. To do this, we divide the slit into odd number of parts. This division helps us analyze how light waves from different sections of the slit interfere with each other. So for instance, consider dividing the slit into three equal parts as shown in the figure. This specific division allows us to calculate the path differences between light waves emerging from different sections of the slit. Now let's focus on the path difference. If the path difference between the ray from point L and point N is 3 lambda upon 2, you can see what is the path difference between the ray from L and from N. Okay, it will be 3 lambda by 2. It should be 3 lambda by 2. Okay, and path difference between the rays originating from L and K will be lambda by 2. And between K and H is also lambda by 2. Between H and N is also lambda by 2. That's why the path difference between the rays originating from L and N is lambda by 2 plus lambda by 2 plus lambda by 2 is equal to 3 lambda by 2. Okay, so it indicates a specific condition for constructive interference. This path difference is essential for identifying the positions of maxima in the diffraction pattern. So finally, consider the path difference Kr. Okay, so which is lambda upon 2. So Kr, path difference, that is the path difference between the waves originating from L and K. Okay, so this means the contributions from the two halves Lk and Kh cancel each other out similarly to how they do in the case of minima. Okay, as we have seen the case of minima, if the path difference between two sections, if the path difference between the wavelets originating from two sections is lambda by 2, they interfere destructively. Okay, so understanding this cancellation help us predict where the bright fringe or maxima will appear in the diffraction pattern. Now delve into the details of how the intensity of a point between the first and second minima is determined. Only the remaining one-third part of the slit, labeled as HN, contributes to the intensity at this point. Okay, other two parts of the slit, so waves originating from other two parts, that is LK and KH, will destructively interfere, and only HN part of the slit will contribute to the intensity or maxima. Okay, so to find the position of maxima, we focus on HN part of the slit. We can divide this section into two equal parts. Further, we are dividing HN into two equal parts. This division is important because it allows us to analyze the path difference between the waves originating from these sections, which is key to understanding the interference pattern. Now consider the path difference between the rays HF and NT. Okay, this path difference is lambda by 2. So path difference between HF and NT, between the rays or waves originating from H and N point, is lambda by 2, where lambda represents the wavelength of light. This specific path difference is significant because it leads to destructive interference. Finally, let's look at the waves from point H and midpoint of H and N. There is we consider a midpoint between H and N. So we have to look at the waves from point H and midpoint of H and N. Okay, these waves have a path difference of lambda upon 4. If path difference between the waves originating from H and N is lambda by 2, then path difference between the waves originating from H and midpoint of H and N is lambda by 4. This smaller path difference results in constructive interference, which is why we observe the maximum at this point. Okay, so these two sections, we have divided HN into two sections. So wavelets or waves originating from these two sections are not interfering destructively. They are interfering constructively. That's why maximum is formed at P point. Okay, so let's consider the distance from H to midpoint of HN, which is A upon 6. Distance HN is A by 3. So distance from H to midpoint of H and N is A by 6. Keep in mind that this distance will help us calculate the path difference between the waves. So what is the path difference between the waves originating from H and midpoint of H and N? Okay, and distance between the point H and midpoint of H and N is A by 6. So path difference will be A by 6 sine theta. Okay, so using basic geometry, we can determine that path difference between the wave from H and the midpoint of H and N is A upon 6 multiplied by sine theta. So we said the path difference equals to lambda upon 4. What is the path difference between the waves originating from H and midpoint of H and N? That is lambda by 4. Okay, which gives the position of first secondary maxima. This equation's A upon 6 multiplied sine theta equals to lambda upon 4 shows us how the wavelength and the angle theta are related to the diffraction pattern. Finally, we solve for the position of maxima with the equation A multiplied sine theta equals to 6 lambda upon 4, which results into 3 multiplied by lambda upon 2, which we considered earlier. This tells us that angle at which first secondary maxima occurs is determined by the ratio of slit width to the wavelength. So let's introduce the equation that helps us find the position of maxima. The equation is sine theta equals to 3 multiplied lambda upon 2a. Okay. Here theta is the angle of diffraction and lambda is the wavelength of light. Okay. And a is the width of the slit. Since the angles involved in the diffraction are typically small, we can make an approximation. This allows us to simplify our calculations. The first secondary maxima, which is first bright spot after the central maxima, can be found using this approximation. So using the small angle approximation, we have theta approximately equal to 3 multiplied by lambda divided by 2 multiplied by a. This simplification helps us easily calculate the position of the first secondary maxima. Remember, this approximation is valid because the angles are small, making our calculations straightforward. So take a look at the image of the single slit diffraction pattern. Okay, so this is the distribution of intensity among the maxima. Okay, so notice how the light spreads out and forms a series of bright and dark bands. Okay, so let's consider an alternative approach to finding the position of first secondary maxima. This approach will help us understand the pattern of light distribution more clearly. So secondary maxima occurs approximately midway between the successive minima. Okay, so this means that after each dark band or minima, there is a bright band or maxima that is not as intense as central maxima. So at the center of the pattern, we have the central maxima, which is the brightest. The first minima occurs at an angle theta approximately equal to lambda divided by a, where lambda is the wavelength of light, a is the slit width. Following the first minima, we encounter the first secondary maxima and then the second minima at an angle theta approximately equal to 2 times lambda divided by a. Okay, so this sequence of maxima and minima continues outwards from the center, showing the periodic nature of diffraction pattern. Now let's determine the position of the first secondary maxima. It will be approximately at an angle theta equal to 3 lambda divided by 2a. This position is derived from the pattern we observe between the minima and maxima. Okay, so the position of first secondary maxima can be expressed as theta approximately equal to 3 lambda upon 2a, which simplifies to 1 plus 1 upon 2 times the lambda by a. This formula gives us precise way to calculate where the first secondary maxima will appear in the diffraction pattern. So let's delve into the general condition for finding the nth secondary maxima in a single slit diffraction pattern. It helps us understand where the bright spots or maxima will appear on the screen. Okay. So the mathematical expression for condition of nth secondary maxima is given by sine theta equals to n plus 1 by 2 multiplied by lambda by a equals to 2n plus 1 upon 2 multiplied by lambda upon a, where n can be positive or negative integers like plus or minus a1, 2, 3 and so on. Okay, here n is starting from 1, not from 0. In the case of condition for nth secondary minima, that is n lambda upon a, and n is starting from 0, and n0 corresponds to central bright maxima. Now for secondary maxima, n is starting from 1, not from 0. Got it? So here lambda represents the wavelength of the light and a is the width of the slit. This equation tells us how the position of the maxima depends on the wavelength and the slit width. Okay, so take a look at the image provided. They illustrate the concept of diffraction through a single slit. Notice how the light spreads out and form pattern of bright and dark areas. Okay, so let's examine the key point about the intensity of secondary maxima. In the single slit diffraction, the secondary maxima are significantly less intense compared to the central maxima. This reduction in intensity is critical because it helps us understand the distribution of light in diffraction pattern. So consider the first secondary maxima. The intensity at point P is contributed by only 1/3 of the slit. For central bright maxima, we considered whole slit, Ln. Now for first secondary maxima, the wavelets from two sections of slit will combine or interfere destructively. Only 1/3 of the slit Ln contributes to the intensity of secondary maxima. This means not all parts of the slit contribute equally to the intensity at this point, leading to a weaker brightness compared to the central maxima. Okay, so notice how the intensity of the first secondary maxima is much weaker than the central maximum. This is because the entire slit contributes the central maximum in phase, resulting in much brighter spot. The difference in contribution explain why the central maximum is the important prominent feature in the diffraction pattern. Similarly, as we move to higher secondary maxima, the intensity decreases drastically. For these maxima, only 1/5, 1/7, and so on of the slit contribute to the intensity. This pattern shows how the distribution of light changes with increasing order of maxima, emphasizing the diminishing intensity as we move away from the central maximum. Okay, so we are going to focus specifically on the intensity distribution in single slit diffraction. As you can see in the images, the intensity pattern is not uniform. Okay, so notice central bright region and the diminishing intensity, the surrounding areas. So let's delve into the intensity of secondary maxima. As shown in the figure, the intensity of this maxima decreases rapidly. This is an important observation because it highlights how the central maximum is much pronounced compared to the secondary ones. So let's focus on the central maximum. It occurs at the angle theta equals to 0. The angular width of this central maximum is given by 2 times the wavelength divided by the slit width, A. Okay, this means the central maximum is the brightest and widest part of the diffraction pattern, which is why it stands out so prominently. Okay, so finally let's compare the widths of central and secondary maxima. The width of central maxima is twice that of secondary maxima, which is lambda divided by A. Okay, this relationship helps us understand the scale of diffraction pattern and why the central maximum is so dominant. Now we are going to explore wave optics by creating and observing diffraction patterns using simple household items. Our objective is to understand how diffraction works and how we can see it in everyday life. Notice the image showing two blades forming a slit, which is key to observing diffraction patterns. So let's start by discussing how you can observe single slit diffraction at home. Okay, all you need are two razor blades and a clear glass electric bulb, preferably one with a straight filament. This setup will help us see the diffraction pattern easily. Next, hold the razor blades parallel to each other to create a narrow slit. Use your thumb and fingers to adjust the blades. The slit will act as our single slit for the diffraction experiment. Now position the slit parallel to the bulb filament and right in front of your eye. If you wear glasses, keep them on to ensure a clear view. This alignment is crucial for observing the diffraction bands. Adjust the width of the slit and alignment of blades until you start seeing bright and dark bands. These bands are diffraction patterns we are looking for, and they demonstrate how light waves interfere with each one. You will notice that colored band appear because different wavelengths of light diffract differently. This is an important concept showing how light of various colors behave uniquely. To make the fringes clearer, you can use filters for both red or blue light. These filters help isolate specific wavelengths, making the diffraction pattern more distinct and easier to observe. Okay, so when both filters are available, red fringes appears wider than blue. Okay, so you will see that red fringes appear wider than blue. Difference is due to the varying wavelengths of red and blue light, illustrating the principle of wavelengths dependent diffraction. So you can recreate Young's double slit experiment by making a double slit in aluminium foil. This simple setup allowing us to observe the interference pattern that are central to understanding wave optics. So we can use a bulb filament as a light source for Young's experiment. This is similar to what we have done before, as it helps us see the interference pattern clearly. Now let's talk about why direct sunlight isn't suitable for this experiment. It's important to avoid using sunlight because it can damage your eyes and won't produce the interference pattern we are looking for. You can recreate Young's double slit experiment by making a double slit in aluminium foil. Okay. So sun subtends an angle of 0.5 degree at the eye. Okay, so an angle of 0.5 degrees is too large to produce clear interference patterns. This is because the light from the sun is not coherent enough to create the distinct fringes we want to observe. Since the sun subtends a larger angle at the eye, it acts as an extended source rather than a point source. This distinction is crucial because only point sources can produce the clear interference pattern we need for Young's experiment. To form clear interference patterns, we need a small point-like source of light. This is why using a bulb filament or a laser is effective. They provide the coherence and point-like nature necessary for observing interference in wave optics. So our objective is to understand how this pattern demonstrates the redistribution of light energy. So in interference and diffraction, light energy is redistributed. Notice how this redistribution is key to forming patterns. It's like when waves in water overlap, creating areas of higher and lower wave heights. Similarly, light waves overlap to form bright and dark areas. Now observe how if light energy reduces in one region, producing a dark fringe, it increases in another region, producing a bright fringe. This shows us the energy isn't lost, it just moved around. Think of it like a seesaw. Okay, when one side goes down, the other goes up, maintaining a balance. Finally, let's connect this to principle of conservation of energy. There is no gain or loss of energy in these patterns, which is consistent with its principle. This means the total energy remains constant, just like in the closed system where energy can change forms but is never lost. Okay, so let's have a quick recap, or let's summarize the points we have studied. Diffraction refers to bending of light waves around obstacles or through apertures, causing them to spread into regions that would otherwise be in shadow. So diffraction becomes more noticeable when size of obstacle or aperture is approximately equal to wavelength of wave. This is why we often see diffraction effect with small openings or edges. Okay. Besides, you can see diffraction in the DVDs. Okay. So you can see in CD, in the brighter part or reflecting part. Okay. In polished part of the CD, you can see there are colored lines, so many colored lines that are due to the bending of light. Okay, that is due to the diffraction. That is a phenomenon of diffraction you can see in the everyday life. So next, single slit diffraction, which is classic example of high diffraction pattern are formed. So when a plane wave passes through a slit width A, it creates a diffraction pattern at a distance D. This pattern is a result of the wave spreading out after passing through the slit. According to Huygens principle, every point on a wavefront acts as a source of secondary wavelets. This principle helps us explain how the wavefront evolves as it passes through the slit. Now let's see the conditions under which diffraction pattern occur. This condition helps us predict where the light and dark bands will appear in the pattern. Minima or dark bands occur at angle where A sine theta equals to n multiplied by lambda. Okay, with n being any integer except 0. This equation tells us where the wave interference cancel out. N equal to 0 corresponds to central bright maximum. Central maxima or less intense bright bands occur at angles where A sine theta equal to n plus half multiplied by lambda, where n equal to plus minus 1, plus minus 2 or plus minus 3, so on. These are the points where wave interference is constructive but not as strong as central maximum. Notice how the central maximum is the brightest and widest part of this pattern. This is because the angular width is given by 2 times the wavelength divided by the slit width, or 2 multiplied lambda upon A. This means that central maximum is where the most of the light energy is concentrated. As we move away from the central maximum, the secondary maximum appears. However, their intensity decreases rapidly. This shows us that light energy is not evenly distributed and the brightness diminishes as we move further from the center. The width of the first secondary maxima is lambda upon A. This is half the width of the central maxima. Okay, indicating that secondary maximum are narrower and less intense. Finally, let's consider how diffraction interference follows the principle of energy conservation. Light energy is redistributed between bright and dark fringes, ensuring that energy is conserved throughout the pattern. So let's start with true or false question. Is the intensity of second secondary maxima greater than the first in single slit diffraction? Think about how the intensity pattern forms and what factors might influence the maxima. Now let's consider what happens when we change the wavelength of light. If we replace red light with violet light in single slit, how does the position of first minimum change? Remember, the point of minima is related to the wavelength and slit width. Okay, shorter wavelengths will affect the diffraction pattern differently. Let's calculate the angle of first minimum for a single slit of width 0.2 mm illuminated by light of wavelength 500 nanometer. Recall the formula for the angle of the first minimum. Substitute the values to find the angle. In this scenario, a single slit produces its second minimum at an angle of 30 degrees with a wavelength of 600 nanometer. We need to find the slit width. Solve for using the given values. Finally, let's discuss what happens to the width of the central maximum when red light is replaced by blue light. Okay, in the single slit diffraction experiment, consider how the wavelength affect the diffraction pattern. Does the central maximum width of the central maximum increase, decrease, or remains the same? Think about the relationship between the wavelength and width of the central maximum. So this is all about today's lecture. I hope you enjoyed the session and understood it well. Thank you.